So, welcome back to day 2 of curve sketching, section 4.5. Now, let's just recall what the steps were. If I ask you to sketch a function, first part, look at the domain. Where is it defined? What x values can you plug in? Second part, what are the x and y intercepts? When x is equal to 0, what's the y value? And when y equals 0, what's the x value? Third part, what sort of symmetry do you have? Is it even? That is, f of negative x equals f of x? Or is it odd, where f of negative x equals negative f of x? What sort of asymptotes do you have? Remember, you have to look at the vertical asymptotes and the horizontal asymptotes. We're not going to concern ourselves too much with slant asymptotes. And then, for the next part, well, let's look at the local mins and maxes. First derivative test there, with the intervals of increasing and decreasing. Using first derivative test, you could get both of those things. And then lastly, what does the concavity and inflection points look like? And that's going to be your concavity test with using the second derivative. So with this in mind, I'm going to do one example, but the worksheet that you have today will give you more practice, as well as the supplemental video that I will have posted on Canvas. So yesterday we looked at a polynomial and a rational function. So there's many more examples we could look at. Like for example, you could look at ones like y equals x tangent x on a restricted domain. Luckily here, the domain is given, and you could go through all the steps. So that we do one example, I will not do this particular one, but know that these examples exist. And one of the particular things you need to look at this example is that you have these endpoints. So one thing that you might want to check is what is the limit as x goes to negative pi over 2 from the right, as well as x goes to positive pi over 2 from the left. That might also help in the curve sketching. But the example I wanted to do today is something that looks like a rational function, but is not quite, because it's not going to have polynomial in the numerator. Let's look at natural log of x over x squared. So if we remember, our first step is, well, what's the domain? Well, for the domain, remember, you can't divide by 0, so x cannot be 0. And the natural log function is only defined when the argument, that is x, is greater than or equal to, or is strictly greater than 0. Not greater than or equals to, because natural log of 0 is where the asymptote from one direction happens. So our domain is going to be open 0, infinity. Okay, so what's next after we find the domain? Well, we need to find the intercepts. So that's, you set y equals 0, and you see what you get. So natural log of x equals x squared equals 0. So natural log of x equals 0, that is x equals e to the 0 or 1. So that gives us the point for intercepts 1, 0. And we can put that over here on our graph. Okay, and then the other intercept is when x equals 0. But that's not in our domain, so we don't need to check that. Okay, after intercepts, you could look at symmetry. But notice the only types of symmetry that I've given you talk about plugging in a negative x. So there's not going to be any symmetry because our domain does not let us plug in negative values. So we can skip right over symmetry in this example. Next, we want to look at our asymptotes. This is where you would want to look at that left endpoint of 0. So let's start out with that. Limit as x goes to 0 from the right of natural log of x over x squared. You could try this by table, just plugging in, making a table and being like, well, here's my x value, and here's natural log of x over x squared. And plugging in values that get close to the 0, and then estimate it. Another way of doing this, though, is if you can remember when you have natural log of x, the limit as x goes to 0 from the right, you know that that's going to give you negative infinity. And the limit as x goes to 0 from the right of x squared is 0. And this thing is just negative infinity. Because when you're doing this division by 0, it will either go to infinity or negative infinity. But since we already have negative infinity in the numerator, we can just say, well, this is negative infinity. You have to sort of reason your way because it's infinity, so it doesn't quite work like a normal number would. So in a way, although it's although it's not approaching negative infinity or positive infinity from both directions, we sort of get this vertical asymptote at x equals 0. So let's draw that dotted line. Okay, so then we can look at, well, what are the horizontal asymptotes? Because within our domain, there's no other random points to the right of 0 that we can just see a vertical asymptote with. It's all defined. So we don't have to do as it goes to negative infinity, but we have to do as x goes to positive infinity. This is going to give us the indeterminate form, infinity over infinity. So by L'Hopital's rule, and that's why we learned it last section, you can take the derivative of the top, derivative of the bottom, and divide them. So simplified, this will be 1 over x times 2x is 2x squared, which as x goes to infinity goes to 0. So we're going to also have a horizontal asymptote at 0. I'll draw as a dotted line again. And that takes care of our asymptotes. Okay, so what's next? We took care of domain, intercept, symmetry, and asymptotes. So next is our derivative test, our first derivative test, and our concavity test, using the second derivative. So to take the first derivative of this thing, you have to use the quotient rule. You can't just take the derivative of top over the derivative of bottom. That's L'Hopital, and that doesn't work for taking derivatives. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over bottom squared. And we can simplify this. X squared times 1 over x is just going to be x minus 2x natural log of x over x to the fourth. We can't do anything with the x inside the natural log, but notice that you're being multiplied by an x term, and there's an x term, so we can factor. And we can cancel to give us 1 minus 2 natural log of x over x cubed. Okay, so what are the critical numbers? Well, if you look at the denominator to find where it's undefined at 0, at an x value of 0, because you can't divide by 0. And you get that by taking x cubed equals 0 and solving. What about saying this equal to 0 and solving? What do we get? Well, that means 1 minus 2 natural log of x equals 0. So our natural log of x equals, well, this is going to be 2 natural log of x equals 1, or natural log of x equals 1/2. That is, x is e to the 1/2 power. So we can make our little chart. And e to the 1/2 power is approximately 1.649. So if that helps us pick numbers. Now notice, you cannot plug in anything less than 0, so that will not be defined. It's not in our domain. So we have to pick something in between here. I'm going to pick x equals 1. 1 is a very nice number for natural logs. And over here, I'll pick x equals 2. So x equals 1, we're plugging it into the derivative. So that's 1 minus 2 natural log of x all over x cubed. Natural log of 1 is 0, so that's 1 over 1 cubed, or 1, which is positive. And then if you take the 1 minus 2 natural log of x and you plug in 2, you're going to get approximately negative 0.386, so that's a negative number, divided by 2 cubed is 8, which is positive. Negative over positive is negative, so you get decreasing. So what's that giving us? Well, if we look at our chart, 0 cannot be a relative extreme value because it's not defined for values less than 0. And it's not in the domain. But e to the negative 1/2, if we look at it, is going to be a maximum. So local max that we have here is going to be this y of e to the 1/2. Okay, so which e to the 1/2, if you're, because it'll be useful later in the graph, that's going to be 0.1839, so a very small value. So that's around 1.5 and then up that much. I'll put it a little higher just so we have a distinction there between our two values we have. And actually, while we're at it, this won't affect it too much, but right now, but let's make this 5, and so this would be 1, 2, 3, 4. 1, 2, 3, 4, 5, just so that we get that scale correct. Okay, and then our increasing, we have that it's increasing on 0 e to the 1/2, decreasing e to the 1/2 infinity. Okay, so now what? Well, we want to do the concavity test, as we said. We had simplified the derivative to be 1 minus 2 natural log of x over x cubed. So to use the concavity test, we need the second derivative. That's the bottom times the derivative of the top is going to be negative 2 times 1 over x minus the top times the derivative of the bottom, 3x squared over x to the 6th. So this is going to be, we can factor out an x squared, negative 2 minus 3 plus 6 natural log of x over x to the 6th, or negative 5 plus 6 natural log of x over x to the 4th. That's only undefined at 0 again. So for possible inflection points, you get 0, and you set that equal to 0 with some algebra that we can do. Let's see, we had negative 5 plus 6 natural log of x over x to the 4th, setting equal to 0. So negative 5 plus 6 natural log of x equals 0. That is natural log of x equals 5/6, or x equals e to the 5/6. So now we just need to test the concavity that we have. This is e to the 5/6, which is approximately 2.301. We can still use this test value of x equals 1. But we need to choose a new one over here. We'll choose 3. You plug in 1 to the second derivative. You're going to get negative 5 over 1, because natural log of 1 is 0. So that's going to be concave down on that interval. And then you plug in 3. And you'll get, if you just plug in to the numerator, you'll get approximately 1.59. And that's divided by 3 to the 4th, which is going to be positive. So that's going to give us a positive number. It's concave up, which means we have concave down 0 to e 5/6, and concave up e to the 5/6 to infinity. So let's plot this thing. Remember, it's going to negative infinity. It goes up, crosses at this intercept. It's still concave down until around here, and it flips. It's concave up. It's sort of, with this scale, it's sort of hard to show, but around here, it flips to being concave up, so that's that upward parabola shaped like that. And going to 0 as x goes to infinity. So that's the example we're going to do. So you can see these examples take some time. So for, say, a quiz or exam, I wouldn't expect you to do too many of these, but definitely expect them to be on the exam. So tomorrow we'll be moving on to a topic called optimization. There will be a worksheet to do before you watch the video. Be sure to do it, and I will see you all tomorrow.